Up until now, we have only described the properties of a system in equilibrium. However, it is important to explain what happens to a semiconductor when it is illuminated. The process of interest is known as photogeneration of charge carriers. Here, electron-hole pairs are generated as light is absorbed in a semiconductor. During the course introduction, we have already mentioned that the mobile electrons and holes are formed in a semiconductor because of light absorption. Now I will explain how this process happens. Here we see a photon incident on a semiconductor. At some point, this photon can be absorbed by the material. Absorption is a process in which the electromagnetic radiation interacts with atoms of a semiconductor, in particular with its valence electrons. This interaction can lead to the liberation of an electron from a covalent bond. If this happens, a valence electron is excited from an energy state in the valence band to an available energy state in the conduction band. It is important to remember that the excitation of an electron to an energy state in the conduction band leaves an unoccupied energy state in the valence band, and this state is then occupied by a hole. Photogeneration results in the generation of electron-hole pairs. In other words, the concentration of mobile electrons and the concentration of holes in the material are increased by the same amount. However, this excitation does not always happen. Photogeneration is limited by energy constraints. To understand these constraints, we need to look at the bandgap energy of a semiconductor. As you recall from our previous video on band diagrams, there are no available energy states for electrons in the bandgap. For this reason, only if the photon energy is equal to or higher than the energy of the bandgap, the photon can be absorbed and an electron-hole pair generated. However, if this requirement is not met, the photon will simply pass through the semiconductor without being absorbed. You may notice that the photon used in this example is red, whereas the photon that was absorbed in the previous examples was blue. This is intentional. Red photons have less energy than blue photons. In this example, the red photon's energy is lower than that of the bandgap. On the other hand, the blue photon has an energy larger than the bandgap. But how do we know the energy of a photon? The properties of the electromagnetic radiation emitted by the sun can be described using the wave-particle duality concept. As a wave, this radiation propagates at the speed of light, and it is characterized by two parameters. The first is the wavelength, which we denote by Greek letter lambda, and it is defined as the distance between the two adjacent wave peaks. The second is the frequency, which we denote with the Greek letter nu, representing the number of cycles per second. The frequency is determined as the ratio between the speed of light and the wavelength, and it is measured in hertz. However, light can also be viewed as a flow of particles called photons. The energy of a photon is directly proportional to the product of the frequency and the Planck constant, indicated by h. Let us now apply these concepts to determine the minimum energy needed to liberate a valence electron in a silicon wafer. The bandgap energy of crystalline silicon is equal to 1.12 electron volts. This is the minimum amount of energy required for a photon to be absorbed and excite an electron from an energy state in the valence band to an unoccupied energy state in the conduction band. We can now apply the relationships we just saw to determine the wavelength of the electromagnetic radiation corresponding to this energy value. Stop the video now and determine the maximum wavelength that silicon can absorb. Now, let's compare your answers with ours. First of all, we need to determine the frequency of light, corresponding to an energy of 1.12 electron volts. We find that the frequency is equal to 2.7 times 10 to the power of 14 Hz. Then we can calculate the maximum wavelength of light that can be absorbed by silicon. it results to be 1107 nanometers. Now let's see what this means when we want to know which part of the solar spectrum can be absorbed by crystalline silicon. In this figure, you can see the spectral power density of the AM1.5 spectrum in yellow. On the other hand, in brown, you can see the fraction of the spectral power density that can be absorbed and converted into electricity in a silicon solar cell. The red dashed line represents the bandgap energy of silicon, expressed in terms of the wavelength of light. Only the radiation at shorter wavelengths carries enough energy to be absorbed and excite an electron in crystalline silicon. Therefore, looking at the solar spectrum, only the part on the left-hand side of the dashed line can be absorbed by crystalline silicon. You may also notice that not all the available energy in this part of the spectrum can be used for generating electricity by a solar cell. This is due to a process known as thermalization, which we will discuss later in this course. As you can imagine, a semiconductor under illumination will no longer be in an equilibrium state. Once illuminated, the number of electrons and holes deviates from their thermal equilibrium values. As these charges are mobile, we need to understand how they move within the semiconductor once excited. And this will be the topic of the next video.